extend to 2D first. If we'll do that before we go to ND. Okay, so what is a system? So 1D system looks like this. Okay, a 2D system. Let me just write this system as a matrix equation. Okay, now this is the most generic equation you can see, but turns out that when you talk about manipulators, you'll see that M12, for example, is equal to M21 and C12 will be equal to C21, and same for K. But let's assume that that's what it looks like. Now let's choose a controller. Remember, for this one, we chose a controller which looked like this. So I'm just going to take this idea and extend it to 2 dimensions. So minus kpq minus kdq dot. Okay, now I'll just write this as a matrix equation. That way you'll understand what those k's are. This will be a kp and kd will be matrices and not a scalar like we had for the 1D case. This will look like this: kp11, kp21, kp22. And then kd11, kd12, kd21, kd22, q1 dot, q2 dot. Okay, let's count the number of unknowns. The free parameters. There are 2 here. In this case, there are 4 and then another 4. So we have 8 free parameters. Okay, so clearly, just like we had 2 parameters, we had 1 equation. So we said that 1 parameter is free, the kp, and kd is a function of kp. If you have 8 free parameters, remember that we're trying to have a critically damped system. So we'll have two equations or 2 conditions. 2 conditions for critical damping, which means that even if we find a relation between those k's, we will have 6 numbers which we have to choose. Now that's just too unwieldy, right? If you try to go to 3 dimensions, you'll see that it will be 9 plus 9, that will be 18. And you have 3 conditions. So 18 minus 3 is 15, so it will be 15 free parameters. So just this method just doesn't scale to high dimensions. So we'll find it very difficult to scale this method as is to high dimensions. So what we do is we will come up with the different methods. Actually, this is known as feedback linearization. You've seen this before in the class where you did differential drive car. We had that equation for control, which was doing the feedback control to draw whatever curve we got. That was actually feedback linearization in the works. So we will circumvent this by using this method called feedback linearization. which is the most common name. The other name for this is control partitioning. I have not seen too many people use the second word, but the first one, feedback linearization, very common. Okay, so let's consider the equation of the manipulator. Okay. What we'll do is we'll choose a torque, and the torque is something which we can tune to whatever you want as m hat minus kpq minus kdq dot plus c hat q dot plus g hat q. So I wrote down m hat, c hat, g hat. These are estimates of m, c, and g. Why do we have estimates? Well, in a perfect world where you design the system in simulation, you know what m, c, and g is, and so you know those values. In a not perfect world or in hardware, m, c, g are parameters of the robot, and it's almost impossible to find the exact values of m, c, and g. So we'll have approximations. Now, just for analysis, we just assume. Let's assume m equals m hat, c equals c hat, g equals g hat. Okay. So if that's true, then what we can do is we can assume those, and then you plug that back in equation. We call that equation 1. So let's put a substitute 2 in 1. We have mq double dot plus c q dot plus g of q equals m kp q minus kd q dot plus c q dot plus, sorry, Mr. Q. Okay, so plus g of q. Okay, now you see that you can cancel a few things. This g will cancel with this g. This c will cancel with this c. And so what you can do is you can move things around. Okay, I'm going to move the whatever is left, the mass times kpq on the left side. You would have q double dot plus kd q dot plus kpq equals 0. And since m is not equal to 0, we can safely say that kd q dot plus kp q equals 0. Okay, so what we've done here is we've sort of eliminated the system dynamics. M is gone, C is gone, G is gone because of the nature of the assumed torque controller. And remember that Kp and Kd is something which you can choose yourself. You can choose whatever you want them to be. So what we'll do here is, since we know that Q is Q1 double dot, Q2 double dot, and so on, and this is generic for n dimensions. We'll actually assume Kd to be diagonal. And we'll assume it to be KD1, 0, 0, so on, 0, KD2, 0. Keep going till KDN, Q1 dot, Q2 dot, Q3 dot, Qn dot. We'll reopen this. Okay, plus KP1, 0, 0, KP2, 0, 0, KP3. Keep going till KPN. Then we have Q1, Q2, so on till Qn. And the right hand side is just zeros. Okay, so that's just what we have here is essentially equations which are decoupled in the sense you can just write n equations, and every single equation is like a spring mass damper equation. So if you want to see it in a much easier way, you can just write it as Q1 double dot plus KP1 Q KD1 Q dot plus KP1 Q equals 0. Q2 double dot is KD2 Q2 dot plus KD2 Q2, and so on till KDN Qn dot plus KPN Q n equals 0. Okay, so each equation is a separate equation. We have n equations. Okay, and now what we want to do is we want to set the constants such that we have critical damping for all degrees of freedom. So what we do is we just enforce that condition equation by equation. So first equation, we want that to be critically damped. For it to be critically damped, we know that the what's the formula? The formula is K. KD is minus C plus 2 square root M K plus KP. Okay, so that's something which I derived earlier. We just need to ensure that this is used for each and every equation. So let's see. For example, if we take first equation, we have KD1 equals minus C. So C here is what's this? It's basically this equation, MQ double dot plus CQ dot plus KQ equals 0. And remember when you put the equals tau, and then remember we did it. We then wrote this as C plus KD Q dot plus K plus KP Q equals 0. So C here is 0 because to start with, there's no damping, right? This system doesn't have damping, but then we did introduce through KD. We also have M, which sits in front of Q double dot is 1, and then K, which sits in front of Q without the controller, KP is going to be 0. So we have KD I equals 0 plus 2, M is 1, K is 0 plus KP is KPI. So we have KPI is 2 square root KPI. Okay, so all you do is once you choose that controller, which I described the feedback linearization controller, Write this equation. Then Kp and Kd can be chosen by this equation. Again, Kp is a free parameter. You can choose whatever you want it to be, and Kd is determined by Kp. So you just do this, and once you do this, you'll see that all the joints are critically damped. And then we didn't have to do much of tuning. We just had to tune or choose one number, Kp. Kd was taken care by. So it's much simpler to do this than to write that equation, which I showed earlier, which had this large number of Kps and Kds. Okay, now one more thing before I show you a simulation is it's a nice thing to try to draw a block diagram for this. Block diagram is one way in which, if you're a control engineer, you will communicate the idea which you have in terms of controller design with someone else. So what the block diagram does is it basically represents these two equations using blocks. We copy those. Okay, so let's draw a block diagram. Okay, so the heart of the block diagram is the system dynamics. I'm going to use a shorthand notation. I'm just going to ignore the things in the bracket. Okay, and from this will spring out Q and Q dot. So why would this spring out? It's because you have a sensor on the manipulator which is measuring Q and Q dot, and that's why it's an output. Now this will have an input. That input would be just one thing, which is the torque. So the input is torque. And now once you have, this is just the equation number one. Now equation number two has to be also shown in the block diagram. So I need to now connect the dots. So I need to take feedback. I need to take Q dot, multiply with the right quantities over there, and that gives me the torque. So you can see that the torque is composed of a summation of few things. So we would have C, G, and somewhere there's M. So M, so we can take these things. We'll multiply that with, so this is Q dot, we'll multiply it with KD. We have Q, we'll multiply with KP. Okay, then we have to sum these. So this is sum. So when we sum, what we want to do is, we really want to sum the negative parts. You can take it like that. And then what comes out of this is going to be exactly what I wrote down here, which is Kp so here, this operation is takes Kd, multiplies with Q dot, and takes Q, multiplies with Kp. But then I take the negative of this, so negative, and I need to multiply that with M. So what I do is I'll get another block, which is M, and then this will produce this mass M times this quantity. I also need to take, I need G, and then G is a function of only Q. So let's take this from here. Okay, then that traps in. Then I need Q and Q dot for C. So Q dot and Q. And then this block will feed into the torque. This block will also feed into the torque. This block will also feed into the torque. And then this is summation. Okay, so the block diagram should convey the same information which is conveyed in those equations. So some people prefer the top one. Control engineers usually prefer the bottom one. I think the first one is more informative. They're drawing these diagrams, but that's how it is. There are some cases where the block diagram is useful, and that usually happens when you have two loops, like an inner loop and outer loop, and then in that case, a block diagram probably wins over the first time. But people have different preferences. Some people just don't like one of the two, and that's fine too. So what this does is this controller ensures that if you have an n-dimensional system, and if you perturb the system, then it springs back to 0, 0, right? That's the goal. I'll show you. I'll just have some code which does this on some hypothetical system where the parameters are just randomly assigned. Okay, so what I did here is I chose M to be a 2 by 2 matrix, C to be another 2 by 2 matrix, and K to be a 2 by 2 matrix. This is just random numbers, not a physical system. You could think that's a spring mass damper system, but I don't really have an animation going with this. What this does is it chooses the KP to be 100 for all the different degrees of freedom. It's just 2 here. KD to be 2 square root KP. I'm trying to do something different here. I'm trying to get the system to go to 0.5 and 0.1. And the way you do this is through a small change in the equations. So remember, this is the equation which I wrote down. The only change I do is instead of having KP times Q, I just put KP times Q minus Q desired. What this does is basically it tries to get the system to Q desired. So Q desired, in this case, my derivation was 0. But if you wanted to go some different set point, just put that set point. So in this case, the set points were 0.5 for Q1 and 0.1 for Q2. And then I think I also have a model uncertainty, which by this I mean that M hat is not exactly M. There is some inconsistency in my estimates of M, which is M hat is different from M. Okay, so let me run this first. Okay, so here you see it goes to 0.5 and 0.1, the red just showing that that's the reference, and the blue is actually the I started at 0, 0, and it goes in spite of this uncertainty. So this, it works. You could change that uncertainty and you'll see that it will not start working because that uncertainty is affecting the system. Now, I think if you also change these gains, let's try 1. And so it just overshoots. Maybe 10 will work. Yes, that's a little better. So here the reason why there's an error in the steady state is because of the uncertainty. If there was no uncertainty, I believe that the error would be 0. Yeah, everything else is very standard here. You need to use ODE. I use ODE integration, and then I just do some plots. Okay, now this is just not a physical system. Let's just think about how we do this for a physical system. So I just took a pendulum, which is the simplest possible system I could think of, and then with the control for that. Let me just write down a few things which is coming up in the animation. So I'm going to do a physical system now. This is the one link pendulum. Okay, so the goal is there's a pendulum of mass m, and this is my theta equals 0, and I'm trying to get the pendulum to go to theta equals to pi divided by 2. Okay, so it's just at 0, and then at the next instant I want it to be at pi divided by 2. So it's just like the simulation I showed you. It was going from 0 to 0.5, 0 to 0.1. For a system like this, so let's write here start is theta is 0, n should be theta equals to pi divided by 2. The system dynamics are okay, very broad. mq q dot plus c q q dot plus gq equals tau, but it's really theta double dot. I think it's ml square theta double dot plus, there's no damping, plus mgl sine theta equals the torque. So I'll have two controllers. You see the difference. So one controller is doing feedback control with no linearization and so on. So Kp equals Q minus Q T minus Kd Q dot, where Qt is reference, which is in this case pi divided by 2. And the second controller does the feedback linearization, which I just talked about. M Kp Q minus Q desired minus Kd Q dot plus C Q dot plus G of Q. Okay, clearly it's simpler than that. C is 0, G is mgl sine theta, and m is ml square. This will be ml square. This will be 0. This will be mgl sine theta. And then we use the critical gains, which we found earlier. Kd is 2 square root Kp. Okay, so I have two different files. This file will do the first controller, which is a position derivative control. Let me run this first. Finished. Okay, so it was very fast, but the plots give you a better idea. Starts with 0 position, 0 velocity, torque is 0, and then it's supposed to go to pi divided by 2, which is 1.57. You can see that theta 1 dot sprints to 10 and then goes to 0, and then the torque is about 250 to 75. Here, what you don't see is, unfortunately, is that behind it is actually the curve, which is actually not exactly critically damped. It actually is overshoots a little bit, I think. Try this. I think this might have an effect. print it after. Okay, so it looks like it's pretty good. You can see it's just right there. Okay, so PD controller actually does a pretty good job here. So all my parameters are set here. There's mass inertia. So my bad. I assume that the inertia is 0. So there's an I term also. So it's serving mass times length squared. It's I plus mass times length squared. I choose KP KD naively 220. This actually is pretty good approximation. Remember that the KD was 2 square root of KP. Square root of 200 is about 1, so 110 times 1.4, so 14. 14 times 2 is 28, so it was very close to the critical damping, and that's why it worked. But if you do, let's say 5, it might actually be a lot worse. This is underdamped. It's wrong. If you increase it to 40, which is, remember, 28 is the ideal, then here it will have, here it's overdamped. So 28 is what is ideal. So in this case, because the way this is set up, the mass actually cancels off with the mass on the other side, the gravity, and sorry, it's really adding that mass term in that equation, which is not here, which is a control partitioning, doesn't really help much. This is the same code essentially. I just copy pasted the entire thing, except that I now account for the torque. It consists of the mass matrix. So the mass matrix, that's the correction. It's not just ml squared divided by 4. It should be I plus account for inertia. And then I think I just assumed it to be a mass in the end, but it's really 0.5 because I assumed that the center of mass is the middle of the pendulum. Yeah. Yes, this is wrong, right? It should be L1. That's good. That's a good catch. Okay, so ml squared divided by 4, and that's because the center of mass is in the middle. I did okay here. Okay. Let me get rid of that red. Let me just make it dark. Okay, so it's spot on. And if you want to decrease this time, you just increase the gains. So that is right here. Set to 200. So if you ramp it up to, let's say, 5 times, so 1000. It's a little bit faster. Yeah, and then of course you can't just keep going it. Somewhere the integration tolerance will affect it. I actually have some other things you can do. You can actually simulate noise. So if you see, so if you put some, so the sensor measures the velocity and position. Now what you can do is you can add some noise to the velocity. So what it does, it takes the standard deviation 0.5, and then it will multiply the standard deviation. Something else. It takes the standard deviation and then multiplies that with finds a normal distribution with mean of θ1 dot mean, in this case 0, and deviation is 0.5. And so if you run this, you'll see that the response will be noisy. So it keeps fluctuating. You can do that too by changing the noise. Okay, and then you can also do that with the torque. If you want to disturb the system using a torque, you can put a deviation. Let's put this to 0 just so that it doesn't affect. You can see it's shaking around. So you can do a lot of things with just